Hello and welcome back to the course. Now we are going to focus on the digital signature schemes RSA. As we already discussed a few algorithms earlier before for making that encryption processes more or to do deep into in certain ways to make it a complex or unidentifying to the attacker. So there are certain developments in 1970s who has made these algorithms more efficient in terms of making this plain text more complex in terms of making implementations on the arithmetic operations. So in Diffie and Hellman were the two researchers who had challenged the cryptography, cryptologists, those who are attackers to come up with the cryptographic algorithm that met the requirements for the public key systems. One of the first of the response to the challenge was developed in 1977 by Ron Revest, Adi Shamir, and Len Edelman at MIT. So first published in 1978. The Revest, Shamir, and Edelman RSA scheme has since that time reigned supreme as the most widely accepted and implemented general purpose approach to the public key encryption. RSA algorithm is nothing but a block cipher in which the plain text and the ciphertext are integers between 0 and n minus 1 for some n. A typical size of n is 1024 bits or 309 decimal digits, and that is n is less than 2 raised to 1024. It makes use of an expression with exponentials. The specialty for RSA is the plain text is encrypted in blocks, with each block having the binary value less than some number n. That is, block size must be less than or equal to log to the base 2 n. In practice, the block size is I bits, where 2i n varying between 2i to I plus 1. So encryption and decryption are the following form for some plain text, plain text block M and ciphertext block C. That is, C can be represented in terms of encrypted, that is block set M, M raised to E mod of n, that is exponential comes into picture. So these are represented with the exponentials. M is equal to C raised to D mod of n, that is mod M raised to E D mod of n. So both sender and receiver must know the value of n. The sender knows the value of E and only receiver knows the value of D. The public key encryption algorithm with the public key of the PU is equal to En and the private key of PR is equal to Dn. For this algorithm to be satisfactory for the public key encryption, the following requirement must be met. So these are the requirements. It is possible to find the value of E, D, N such that M raised to ED mod of n is equal to M for all m less than n. Second is, it is relatively easy to calculate the mod m raised to E mod n and C raised to D mod for all values of m less than n. So it is infeasible to determine D given E and n. Now we are going to focus on the first requirement, considering that rest of the questions later. We need to find out the relationship of the form m raised to ed mod of n is equal to m. So preceding relationship holds if E and D are multiplicative inverse modulo phi of n. So where phi of n is a Euler's Tortian function. The relationship between E and D can be expressed as ed mod of phi of n is equal to 1. So E and D are multiplicative inverse mod of phi of n. According to the rules of the modular arithmetics, it is true only if D and therefore E is relatively prime to phi of n. We are now ready to state the RSA scheme. The ingredient for the RSA's algorithm are PQ, two prime numbers, that is private chosen, n is equal to PQ, that is public calculated. That means there is a public key and it is calculated, not chosen. Okay, so E with GCD phi of n E is equal to 1, that is E varies between 1 to phi of n, which is a public and chosen. D e raised to minus 1 mod of phi of n. So this is a private and it is calculated. So these are the four ingredients for this particular algorithm. The private key consists of Dn and the public key consists of E of n. Suppose that user A has published its public key and that user B wishes to send the message M to A. Then B calculates ciphertext, that is C is equal to M raised to E mod of n and transmits C. On receipt of this ciphertext, user A decrypts by calculating M is equal to CD mod of n. So this is a generalized sequence for the RSA algorithm. We can say this is a summary for the key generation by Alice, encryption by Bob with the Alice public key, and decryption by Alice with the Alice public key. So this is a problem of the example taken and the communication between Alice and Bob. So select PQ. We have to choose PQ. P and Q both prime. P is not equal to Q. This is a condition. Second, calculate P into Q. Calculate phi of n. P minus 1 into Q minus 1. Then select in integer E. That is GCD phi of n. E is equal to 1. That is E between 1 to phi of n. Calculate again D. D is equal to e raised to minus 1 mod of phi of n. Public key and private key. PU and PN. This is a key generation by Alice. Next is encryption by Bob with the Alice public key. Plain text is M, which is less than n. Ciphertext is C is equal to M raised to E mod of n. This is the encryption by Bob's with Alice public key. Then decryption by Alice with the Alice public key. Ciphertext C, plain text M is equal to C raised to D mod of n. So these are the overall summary or the steps which are involved into the RS algorithm. For example, RSA algorithm works with the plain text, suppose 88 as an input for the encryption. It is raised to 7 PU length 7 88 raised to 7 mod of 187 is equal to 11, which is a ciphertext length, which is again given to the input as a decryption. For the decryption block, then 11 raised to 23, that is PR key length, private key length, and mod of 187. It gives a 88. So again plain text is being recovered. So arithmetic operations are being made, and because of which we can say encryption decryption process is there. For the same example, we can say this Alice and Bob generate. Alice generates a public as well as private key pair. Bob encrypts using the Alice public key, and Alice decrypts using the her private key. For this example, the key is generated as follows. Select two prime numbers. P is equal to 17, Q is equal to 11. Calculate N is equal to PQ, that is comes into 187. Calculate phi of N. P minus 1, Q minus 1, that is 16 into 10, that is 160. Select such E relatively prime to phi of n is equal to 160 and less than phi of n. We choose E is equal to 7. So determine D such that DE D1 mod of 160 and D is less than 160. The correct value is D is equal to 23, because 23 into 7 is equal to 161, that is 1 into 160 plus 1. So D can be calculated using the extended Euclid's algorithm. The resulting keys are public key PU is equal to 7 187 and private key 23 187. This example shows the use of these key for plain text input of M is equal to 88, as we have seen in the block diagram. For encryption, we need to calculate C is equal to 887 mod of 187. Exploiting the properties of the modular arithmetics, we can do this as follows. 88 raised to 7 mod of 187, and that is equal to 88 raised to 4 mod of 187 into 88 raised to 2 mod of 187. So 88 raised to 1 mod of 187 mod of 187, that gives a 88. 88 raised to 2 mod of 187, it gives a 7744 mod of 187, that is equal to 77. And for 88 raised to 4, this calculation gives a 132. 88 raised to 7, it gives a 11. So this kind of arithmetic operations are there. For decryption side, this is at the encryption side. Now this, at the decryption side, we calculate m is equal to 1123 mod of 187. So 11 raised to 23 mod of 187 is equal to this calculation 11 raised to 1 mod of 187, 11 raised to 2 mod of 187, or 11 raised to 4, 11 raised to 8, 11 raised to 8 mod of 187. Total raised to total into mod of 187. So one by one, it gives a 11, 121, 55, 33, 187. Sorry, 88. So ultimately, it gives a 88 as an output at the decrypted at the decryption. Ultimately, it gives a plain text of length 88. We know we were going to look at the example which is given in the, by the Hell in 1979, which shows the use of the RSA to process the multiple blocks of the data. In this simple example, the plain text is an alphanumeric string. Each plain text symbol is assigned a unique code of 2 decimal digits. A is equal to 0, A is equal to 26 raised to 6. The plain text block consists of the 4 decimal digits or 2 alphanumeric characters. So this is all about the implications of the RSA algorithm. Thanks for watching.